Okay, so I have been talking about two types of problems problems related to rigid body dynamics. I have done preparations to be able to handle those two types of problems. I have derived two versions of MESA, which I have called as version 1 and version 2. I want these versions to be ready with me because it saves time to start solving the problem. If you do not start with these versions, you will have to start with the vector equation, MESA vector equation. Converting converting that vector equation to scalar equations will always take some time. We don't want to keep repeating that every time we solve a problem, and thus I have made ready two scalar versions of MESA. That is the motivation. What are the two versions? Let's recap. I was I derived these things last time. I gave some explanations also. I feel like going over that once again to give you full clarity on what those types are and how those two types are different from each other. So in type 1 problem, the angular velocity of the body with respect to an inertial frame omega mi, you can say that the expression can always be written as a scalar times E hat, and that E hat could be something like this. After all, omega mi is a vector, and one can always say that you can find that direction E hat and then say that the vector will be a scalar times that vector. However, in type 1 problem, it is not clear whether the rate of change of that vector E hat with respect to I is 0 or not 0. It is not clear. And the moment you realize it is not clear, you should deem that problem as a type 1 problem. In contrast, type 2 problem will be such that you will be able to write omega mi as a scalar times E hat, and then you also have the clear realization that this vector this vector E hat, whatever it is not changing with respect to the I frame. d E dt is 0. That realization is very clear, and the moment that realization becomes clear, the problem 2 can be classified, the problem in hand can be classified as a type 2 problem. Okay. Now, if omega mi is omega E hat, where dE hat dt is 0, it also implies that whenever required to find the angular acceleration of the body with respect to I frame, that can be written as this, where omega dot means the scalar derivative of, or the derivative of the scalar omega. Here it is not clear. Here you don't know whether omega mi is equal to omega dot E hat or not. Not clear. And as I said, if it's not clear, you deem that problem as a type 1 problem. Okay. Now, in type 1 problem, once you have identified the problem to be a type 1 problem, you will choose a point A which is fixed to RB. Okay. And you will have a coordinate system the working coordinate system will be this, such that these three axes are the principal axis. P axis of RB at point A. In type 2 problem, you will again identify a point A which is fixed to RB. You will also have a working coordinate system which I denote using the same notation x1 e1, x2 e2, x3 e3. But then here these axes need to be fixed to RB, but they need not be the P axis. Need not be the P axis. In fact, you will choose E3 in your coordinate system will be same as E hat. What is E hat? E hat is the direction along which omega mi is oriented. This is how we want to set our coordinate system. So in both cases the axis will be fixed to the RB, but in type 1 the 3 axes are also the principal axis. In type 2 the 3 axes need not be the principal axis, but I will choose my E3 direction here to be the same as the direction along which the body is having its angular velocity. Okay. What else? Is there any other distinguishing feature? Just let me this. The system may or may not be here. Yes, one more thing I want to mention. In both cases, choose A to be a valid point for MESA. This applies to both. Both cases ensure that A is a valid point. Type 1 problems, type 2 problems. All right. In both cases, both type 1 and type 2, you will apply Euler's first axiom. Generally speaking, it will be required to apply first axiom also, and that will result into 3 scalar equations generally speaking. Same thing here, 3 scalar equations. Generally. What else? In both types of problem, you will apply MESA equation, but the versions will be different. For type 1 problem, I will apply what I call as the version 1 of the equation. I am going to write it, and I hope it helps you recall what I did last time. This is the version 1 equation where ma is the net moment external force system about point A. Okay, and this is being expressed using the working coordinate system as MAE1, MAE2, MA3E3. And this set is a set of 3 more scalar equations. So in total we have 6 equations, 1 and 2 combined. I mean Euler's first and second axiom combined. Now in version 2, the Euler's second axiom, or MESA, looks like the following. MA has the same meaning, the wordings are the same what I wrote, same as on the left hand side. Type 1, type 2. Okay. So this was the recap coming from the previous lecture. In the last tutorial class, I started solving this problem. There is an L-shaped rod given here. At A, it is supported by a kind of connection, which I will describe again. And then this rod is free to move the way it is shown. I mean, this is the way it is moving, rotating about a vertical axis. Okay. So T is an applied torque. What else is given? It is given that omega mi is omega times E hat. What is E hat? E hat is this direction. And it is also given that d E hat dt is 0. The direction of E along which the angular velocity is oriented is never changing its direction, as seen by whom? As seen by I frame, as seen with respect to I frame. The rods have length, They have lengths L, both have L. Mass is M, M and M. Length is L and mass is M. Okay. It's also given that there is gravitational force acting downwards, and then it is given that the support resists displacement of A in all three directions. All three directions, horizontal, vertical, all. Support also resists rotation of RB in all directions except E hat. So except this direction, all other angular velocity components will be resisted by the support. This is what is given. What do we have to find? We have to find the action force system at A, and I also have to find omega dot. This is what is the problem statement. Solution. Step number 1. First you judge whether it is a type 2 problem or type 1 problem. The judgment comes from what? The judgment comes from here. Since it is given that the angular velocity is omega E hat and E hat does not change with I, it falls in the type 2 category. Type 2 problem. What is step number 2? Step number 2 is to identify your working coordinate system. Guidance is choose the origin to be a point fixed to RB and about which MESA V2 will be written. The origin should be a point fixed to the RB and MESA V2 also will be written about that, which means that A should also be a valid point. Whichever point you are choosing to be the origin, it should also be a valid point. So the working coordinate system that I am going to use here is, and also the axis should be valid point. One more line. And axis of WSys should be fixed, should be M fixed, and E3 should be E hat. So the working coordinate system origin should be fixed to RB. Origin should be a valid point. Axis must be fixed to the RB. Axis means x1 e1, x2 e2, x3 e3. These must be fixed to the RB. One more point I wrote here. And you should make sure that x3 e3, or rather 3 axis, should be along E hat. Ensuring all these, let me call it 1, 2, 3 and 4, I choose the working coordinate system to be AX1 E1, X2 E2, X3 E3. Note A is a valid point because A is fixed in I. A is the support. A is where the support is, here. Okay, and since A is fixed in I, AI will be 0. That is why the extra baggage term that appears in MESA will be 0. Okay, so this is my working coordinate system. Shown here in green color. X1 E1 and X2 E2 are making a horizontal plane. To help you visualize, I am saying this. I have drawn the axis in a way such that X1 E1 X2 E2 make a horizontal plane. And X3 E3 is of course vertical, that is clear from the diagram. So I have identified a working coordinate system. Step 3, free body diagram. This is the force system that will emerge, or that is there at support A. I explained this in the last tutorial also. Why I am putting R1, R2 and R3. Why am I putting CR1 and CR2, and why I am not putting CR3. It is a given information. The support does not resist rotation about 3 axis. Okay. What else? There is an MG coming here, and there is an MG coming here. Now, referring to this coordinate system that I have shown here in green color, if I have to write the coordinates of various points, A will have of course coordinates 0, 0, 0. This point, which is the center of mass of the vertical rod, will have coordinates what? Will have 0, 0 minus L by 2. And this horizontal rod will have coordinates L by 2, move in this direction. No, it will be 0. First coordinate will be 0. It will be 0, comma L by 2, comma minus L. R1, CR1, R2, R3, CR2, 0, 0, minus L by 2, 0, L by 2, minus L. Step 3. What is step 4? Step 4 is apply Euler's first axiom. Euler's first axiom means net force equals 2 times m. It's the total mass of rod. total mass of L-shaped rod multiplied by acceleration of g with respect to I. What is g? G is the center of mass of this RB, which is lying somewhere where I just put g on the figure. Okay. Now the center of mass of the rod can be, or the acceleration of the center of mass can be computed like this. For a composite body, so one is vertical rod, two is horizontal rod. Ci is the cm of the ith rod. Mi is the mass of the ith rod. So I can write AGI as 1 by 2m m a c 1I m a c 2I. But AC1I is always 0. Lies on the vertical rod. Actually, the vertical rod is the axis, instantaneous axis of rotation. AB is the instantaneous axis of rotation of L-shaped rod. It means AGI is simply m by 2m AC2I, and AC2I I am going to write directly as omega square L by 2 minus 2 minus E2 and omega dot L by 2 along minus E1. Okay. Now this is something that can be obtained using acceleration transfer relationship, or if you are able to visualize directly, it will follow omega square L by 2 E2 minus omega dot L by 2 E1. So going back here, star, going back to star, what I have is F net equals 2m times half minus omega square L by 2 E2 minus omega dot L by 2 E1. Now F net, if you go back to the free body diagram that I showed here, F net will take contributions from what? It will take contributions from R3, R2, R1, this mg and this mg. Now on this I actually forgot to put T. I should have. Applied torque should be put. But it doesn't contribute to any force. So I am going to write F net as R1 E1 R2 E2 plus R3 E3 minus 2 mg E3. That is my F net, and that must be equal to minus m omega square L by 2 omega dot L by 2 E1. I will match the coefficients of E1 here to whatever is appearing along E1, which is this. I'll match the coefficient of E2 to E2 here. E3, E3, there is nothing along E3, so that should be 0. Let's write the expressions here. This is what should follow. Mg. So if you go and check what they were asking us to find in the beginning, they were asking us to find the reaction force system at A, and they were asking us to find omega dot. Now what have we achieved so far? I have been able to find R3 is 2 mg. Okay. I have been able to relate R2 to omega. I have been able to relate R1 to omega dot. Have I found R1, R2? No, I have not, because I don't know what omega and omega dot is. But once I am able to find omega dot down the line, I can come back and these equations will help me find R1 and R2. So I keep these equations in reserve for the time being. So Euler's first axiom, done. Now I am explaining things step by step. Why am I doing it? Because I want you not only to learn how to solve this equation, but also see the approach that will be applicable to other problems also. So these steps, if you understand, you kind of remember the flow chart, what steps to take one after another, you should be able to solve many difficult problems, many seemingly difficult problems. Okay, so step 4, Euler's axiom applied. Step 5, Euler's second axiom. Right here, step 5. Euler's second. Euler's second means MESA. And MESA, in MESA also I know I am going to apply V2 because I have already recognized it in the very beginning that this is a type 2 problem. Since it is a type 2 problem, I have those equations handy with me. These are the equations. Again, I will have to write. I mean, I have written this earlier also 2 slides ago, but I don't have a choice. I823 omega square Ma2 I823 omega dot plus IA13 omega square MA3 equals IA33 omega dot. Okay, let's work on the left hand side first. So left hand side is what? MA, the full vector, and that we are writing as MA1 E1, MA2 E2, and MA3 E3. Now if you go back to the free body diagram, we should be able to write MA vector as CR1 E1, CR2 E2, and T times TE3. This is the applied torque. And the way it was applied, it is actually along E3. Let us go back and have another quick look at the free body diagram. This is the free body diagram. So if I have to find the moment of the net moment due to this reaction, due to this force system, net moment due to the external force system about point A, mind you, R2 does not give any moment because it passes through A. R3 and R1 for the same reason do not contribute to any MA. So what contributes? What contribution is CR1? The other contribution is CR2. The other contribution is T. Another contribution, some contributions can come from these mg's. Well, this mg what I'm showing here, it passes through A, that also doesn't contribute. There should be one contribution coming from this mg. Does this offer any moment? Is there any moment due to this force mg? Yes, there is. It is mg times L by 2. That also should be added. And moment due to mg, this mg will be along one direction, right? So it should be mg times L by 2 right, mg times L by 2 along E1 direction. That's the moment about it. I'm going to add this on the later slide, but let's make sure I'm not missing anything. R1, R2, R3 do not contribute, CR1, CR2 included, T included. This mg does not contribute any moment. This mg generates a moment which is mg L by 2 times E1. Let's go back and write this here. And I think that is negative actually. This should be negative, should come with negative sign, minus mg by 2. Okay, so I'm going to group coefficients together, so I get CR1 minus mg L by 2 E1, CR2 E2, and T E3, which means what? It implies that MA1 is CR1 minus mg L by 2, the same MA1 that will go and be the left hand side of this equation, that is CR1 minus mg L by 2. MA2 will become CR2. Okay, and MA3 will become simply T. CR1 minus mg L by 2, Ma2 is Cr2 and Ma3 is T. Okay, so the left hand side, okay, I have found the expressions for the left hand side. Now let's go to the right hand side of this. Now the right hand side requires us to find some inertia components. How many of them? The same, 3 of them. Again, out of 6 components, to solve this problem, I need only 3 components of the inertia matrix. So need not worry about all other 3 components. So my next task is find 1, 3, 2, 3 and 3, 3. Now in this problem, IA13 is 0. Why? Because entire RB lies in X2 E2 X3 E3 plane. We need to find 2 other inertia components. Let's find IA13 first, or rather IA33. Now before I start finding IA33, let us locate where the centers of mass of the 2 parts of the RB are lying. So this is A, this is 0, 0, 0. C1 is 0, 0 minus L by 2 and C2 is at 0 L by 2 comma minus L. Okay, axis orientation are visible here. So I'm going to write these coordinates in this form: XC1, XC2, XC3 equals 0, 0 minus L by 2 and XC will be slightly longer. Let me keep it like this. We will refer to these 2 directly. Finding IA33. IA33 I will write as I of part AB is the vertical part about its own center of mass 33 plus M of M times, which is the mass of the rod, each of the rods, times XC1 square plus XC2 square. That would be 0 plus 0 square. Now how am I writing 0 plus 0 square? I am referring to this. Similar problem I saw yesterday during the tutorial session. I hope you have understood, and that is why I am writing it directly. 0 square, 0 square. I hope you will be able to figure out why it is 0 square plus 0 square. Further, if you look at the vertical rod AB, IC133 of AB would also be 0. Why? Because it is a thin rod and the axis 3 is along the rod itself. Thin rod and E3 is along the rod. So there is no moment of inertia. So this is IA. This is of AB I'm talking about. I should have written here IA33 of the whole body. I am going to find in two parts, IA of AB and then IA of BD. I should have written it earlier. IA AB is 0. Call this as a known quantity. IA CD 33. This I will write as IC2 CD 33 plus mass of the horizontal rod, this one, and then I am going to again put some numbers here directly. Which I am picking up from here. This comes from here. These coordinates. Okay. Now what is ICD33 about its own center of mass? That is going to be ml square by 12. So we have this and this, ml square by 4, and that gives me CDIA33 as ml square by 3. Okay. So I have taken care of this. This is actually 0. I have found IA33. Next is to find IA23. IA23. Finding IA23 of the RB. I'm going to write this for the two separate parts for AB and CD. Okay, for AB, I'm going to write this as parallel access theorem. IC123 minus m times 0 comma minus L by 2. I will leave you to figure out why I am writing this. I believe it is correct, and it comes from again these coordinates that I have identified for the two centers of mass. So according to me, I AB A23 is a AB I of the same body at C1 minus M0 minus L by 2, and then so clearly this is not going to contribute anything, but then the question is, what is I23 of body AB about its own center of mass? That is also going to be 0. Why? Because p-axis, something to do with p-axis. That's the hint. Okay, something to do with p-axis. So this is just 0. Let's have a look at same component of inertia matrix about BD going to be written as IC2 23 minus M times two things multiplied, and those two things according to me are L by 2 and minus L. These two coordinates being used, these two coordinates, L by 2 and minus L. Okay, whereas this is again 0 because of the p-axis involvement, and this becomes plus ml square by 2. Okay, so this is known, this is known. I get IA23 as 0 plus ml square by 2, ml square by 2. So IA 23, 13 and 33 all unknown. Go back to MESA V2 which I left here, this equation. Let me call it as star. So in the star equation, right hand side IA13, IA23, etc. Now I can write in terms of mass of the rod or mass of the individual rods and lengths of the individual rod. So ml square by 2, such terms will appear on the right hand side, and of course there will be the unknowns omega dot and omega appearing on the right hand side. Left hand side I am going to replace MA1, MA2 and MA3 in terms of what I had written earlier here in terms of CR1, CR2 and T. Okay, so if you put everything back in this equation and try to simplify the algebra little bit, you are going to get these equations, which I leave for you to be verified. You will get these equations. CR1 minus MGL by 2 turns out to be minus ML square by 2 omega square. Okay, CR2 turns out to be ML square omega dot by 3. No, not right. CR2 turns out to be ML square by 2 omega dot. Okay, then I get the third equation as T as ML square omega dot by 3. So these are coming from MESA V2 equation set. All right. Now the third equation is of immediate interest to me. Why? Because this equation can be solved directly to get omega dot. Omega dot turns out to be 3T by ml square. They wanted us to find it. This becomes an answer right away. One of the answers. Now they also wanted us to find CR2 and CR1 and so on. CR2 can also be found. CR2 is also coming directly. CR2 is ml square by 2 omega dot, right? ml square by 2 omega dot, which is 3T times ml square. Okay, so this turns out to be just 3T by 2. 3T by 2 CR2. CR2 is 3T by 2. Is it dimensionally sound? I think so. T is torque, and so is CR2. So we are fine. I'll give you a break. Let me finish this problem and then I'll let you have a break. Omega dot and CR2 found. What else they wanted us to find? They wanted us to find CR1, and then they also wanted us to find R1, R2 and R3. If you recall, R3 was found as 2 mg, so R1, R2 is left there and CR1 is left here. Now you see, CR1 depends on omega, angular velocity. Do we know angular velocity? No, we do not know, but we know angular acceleration, omega dot. Let's integrate and get omega, right? That's straightforward. Let's do this. So omega dot turned out to be 3t ml squared. Now t is a constant. They told us in the beginning. It's given in the problem. Given info. I'm just going to integrate. Omega becomes 3t ml squared times t plus omega naught. Was there any initial condition given? Well, I didn't write it, but it seems the original author of this question, he had given us omega at t0 is 0. It's a given information, which I should have included on the very first slide. I did not, but I am telling you now. It is given, and that's why it turns out that omega will be 3t ml square times small t, which is time. Omega naught is 0. Once you have omega, then everything will be found. CR1 here, I am going to take mgl by 2 on the right hand side. I know omega, CR1 will be found, and if you go back all the way to reaction forces, here also you see that R3 equals 2 mg was found, as I was saying a little while ago. R2, once omega is found, you know R2, and omega dot is found, so you know R1 also. So now we are in a position to find all the unknowns that we were asked to find. I am leaving the few steps of algebra for you to work out. I am giving you the final answer. MT R1 turns out to be minus 3t by 2l. R2 turns out to be minus m omega square l by 2. And R is already 2 mg. And CR1 is mgl by 2 minus ml square omega square by 2. Should have been written CR1. No. Omega has been found, so I am going to write it as mgl by 2 gl by 2 minus ml square 3 tt ml square whole square. CR2 turns out to be 3 by 2, and CR3 is of course 0. It's not an unknown. So I have all the unknowns I have found. R1, R2, R3, CR1 and CR2. verify. Alright, we take a break.